Oh, yeah.
So thank you very much. I'm going to talk about this stripe structure that develops on a rough inclined plane when a granular material is flowing down. In the first part of my talk, I'm going to talk about experimental results that were partly obtained during my stay as a postdoc in Los Alamos. And then I'll show you results of numerical simulations obtained by Jim McElwain here that nicely match up with the experimental observations. Moreover, they help us to look inside what happens in this instability. So this is our system. The granular material is flowing down this inclined plane. And in the stationary regime, we find that these longitudinal stripes are formed. As a function of the plane inclination and Hopper opening, this phase diagram shows that these stripes are actually present in a quite broad range of this phase space. And we all know that when we increase the plane inclination, the mean density of the flow is decreasing. So actually, this region for the stripes spans a quite wide range of the mean flow density. And this phase diagram was obtained for a plane length of 2 meters. Actually, if we increase the plane length, we can push this border here towards the denser regime. So this is our longest plane we have been played with, almost 6 meters. And then we got the stripe state for sand down to 36 degrees. In this normalized units for the plane inclination, that means 1.5 times for the tangent of the angle of the inclination times the tangent of the angle of repose. So now we are interested in the dense regime. So I'm going to analyze the structure of these stripes in the dense regime. But before going there, let me quickly remind you about what happens in the dilute regime, which was nicely explored by Olivier in this work. So here, the mean packing fraction of the flow is below 0.3, which is quite dilute. And already before the instability, there is a variation of the density in the flow, so that near the plane, you got the lowest density, and on the surface, you have the highest density. And then the dense surface region starts to sink, as it is shown here, and the fluffy region from the bottom starts to rise, just like in the Rayleigh-Bénard instability for liquids. And we got this vortex-like structure on the plane. And one peculiar feature of this structure is that there is a surface velocity modulation. So the velocity at the surface is higher here in these regions where we have the valleys, and lower where we have this height maxima in this flow. So let me now go to the dense regime immediately by showing movies what we see there. So as you see here, there are these height maxima, which I hope you see are going much faster than the material in between. Here's another movie taken at a higher frame rate. This shows a little bit more clearly that these regions move faster than in between here. And if you look carefully, you might even notice the lateral migration of the grains. I play this movie once more. You might notice that actually the grains are migrating towards these fast-moving regions. Do you see that? So now here is the two structures. This is what I have shown earlier for the dilute regime. And this is what we have now for the dense regime. Quite different, isn't it? So here you have this height maxima, which are moving fast. And actually, they correspond to a dense region here on the surface. And the circulation goes this way. So I'll play the movie once more. And then, if you increase the plane inclination, the same setup, you get that those height maxima suppressed by the emergence of these fluffy regions, which are here, and the flow remains fast in between them. Let me play that once more. Get it? So now we have observed these two regimes for a variety of materials. Here you see two sand. This one is more angular. This one is from one of those booming sand dunes where the grains are rounded. We got glass beads. We got very anisotropic particles of copper and spherical copper beads. And for all of these materials, we got both regimes. So here, for lower plane inclinations, we got these fast, dense plugs for all of these materials. And if we increase the plane inclination, we got into the other regime where those plugs are suppressed by the emergence of the fluffy region in between them. So this is how we measure the mean density of the flow. We have this setup in which we shine a laser, and by the shift of the laser spot here on the surface detected by this camera, we detect the flow height. And during stationary flow, this is a signal of the flow thickness that we have. And then we abruptly decrease the plane inclination, and the flow, everything freezes. And then we have the static height. The ratio of these two heights is the normalized mean density of the flow, which is decreasing with increasing plane inclination. This is a lot of data collapsed for different materials. They nicely collapse, so we get a good curve describing this density decrease generally. So now for the dense regime, for the stripes in the dense regime correspond to a mean density between 0.6 and 0.95, which corresponds to a normalized plane inclination of starting at 1.25 up to more than 2. And then for the dilute regime, we got the mean density between 0.2 and 0.7, corresponding to this normalized plane inclination. So now I have here the experimental evidences showing that we have this structure. We got a velocity modulation. We measured the lateral velocity. I'll go quickly through all this in the interest of having time for the molecular dynamics results. So we see that there is this convection. We measure the velocities also at the top of the layer, but also from below through a little window. So we get evidence for these red arrows for the migrating velocities here. And then we detect with our laser line the surface. You see that these regions where the flow is dense, the laser line is very sharp. And here, this is the experimental evidence that the surface is fluidized much more in between. These are the velocity profiles. The velocity, the instability is only occurring above a certain thickness of the flow, and then above the other critical thickness it disappears. The wavelength is about 3 to 4 times the thickness of the flow, and this is the critical thickness above which we have this instability. We also measure the pattern in transmitted light, and from that we can know that below this dense region there should be a dilute region, as the light absorption has this double component. So just one more slide showing the transition between the dense and dilute regime. As we go from here to there, in between the fast moving regions, the fluffy region emerges more and more and suppresses these peaks here. And now let me show you the results of the numerical simulations obtained by Jim. So the first plot, these are all cross sections of the flow. The first plot is the packing fraction. Here you see this dense part on the top of a very fluffy region. And the velocity plot this is the downstream velocity, shows that effectively this dense region slides very fast compared to the neighboring part. And this is the circulation, a very slow circulation of the grains inside this flow. And the more interesting stuff comes here. Here you got the inertial number. So you see very high shear, very high inertial number below this plug. And inside the plug, the velocity gradient goes down, and the inertial number is the lowest here. So now we can measure from these plots how the packing fraction changes with the inertial number in this whole domain. And it's a surprisingly very sharp, very nice curve. And the second thing is the friction, the effective friction as a function of the inertial number. And we see this turnover here, which we believe is a key point for this instability. So as the thickness of the flow is increased, at a certain point, we arrive to a point where this curve turns over. So at the bottom of the flow, we reach the maximum, we reach this inertial number, and then what happens is that our flow structures itself into two regions. In here, the inertial number is decreased so that we go back on this curve, and in below, the inertial number is increased further so that we go downwards this way on that curve. So somehow the flow optimizes itself into moving into a lower friction configuration. And the critical inertial number is about at 0.7 from the simulations, as you see here, and that nicely matches with the experimental data. So there seems to be a quantitative agreement on this here. Before the conclusions, let me just show you a movie of the molecular dynamic simulations. Here, the color code is just the velocity, the downstream velocity. You see this fast-moving region in between this. So summary, we see a new structure as compared to the dilute regime reported earlier, where the thicker parts move faster, and we have verified this for various materials, that the density range for this structure, mean density always is in between 0.6 and 0.95. And from molecular dynamics simulations, we see how this structure evolves as a consequence of this curve for the effective friction. You could think in terms of a Leidenfrost effect, where a liquid drop is just hovering above a hot plate, while the friction is reduced between the liquid and the hot plate by the evaporation of this drop. Thank you very much. Yes.
These are very steep flows. I mean, you're driving this flow very hard.
In a certain sense, steep, but I have shown in the beginning that we went down to 1.25 as for the dimensionless inclination.
I was responding, I think, to 52 degrees. For
No. So those 52 degrees was the dilute regime, and for sand, the lowest we can have for the instability is 36 degrees.
Okay,
for sand,
which is not so great. Yeah.
For sand, that's not very steep. And obviously for glass beads, the corresponding inclination is much lower, something like 26. Okay. So those are not steep.
So not so strongly.
So those are very, at the beginning, in the initial state, those are very dense flows. Yes?
Can you express a sort of an understandable physical explanation of why in one type of flow the thicker bits move faster, and in the other type of flow the thicker bits move slower?
Well, there is a continuous transition between the two, and I cannot say more than what is shown here. that as you get more and more fluidized, this region just increases and turns over, and that mechanism where the heavy stuff would like to sink and the fluffy stuff would like to rise gains over the other mechanism which is present in the dense regime. In the dense regime, obviously something else should be there, because in the dense regime we got the height maximum corresponding to the fast moving region where the flow is actually downwelling. So if you would have that force, then you wouldn't have a height maximum there. So there is a difference in the mechanism between these two
You
regimes.
say mu, the mu as a function of I is responsible for it. Is this
Yes.
the claim?
Yes.
That's what we said.
Yes.
Okay.